Hello, Geometry Honors. Well, today we're looking at lesson 10.3, Apply Properties of Chords. And yeah, all about chords today. There's a little bit of recall here. A chord is a segment with endpoints on the circle. And when you think about that, if you have a chord, it's going to divide the circle into two arcs. And one's going to be major and one's going to be minor, unless, of course, the chord happens to be a diameter, in which case it's going to split the circle evenly into two semicircles. The first theorem we're going to look at today says, well, let me get it down here. In the same circle, or in congruent circles, two minor arcs are congruent if and only if, so that means it's going to be true frontwards and backwards. The statement's going to be true. Also, its converse is going to be true. If and only if their corresponding chords are congruent. And I think that makes pretty good intuitive sense there. So in the same circle, if chords are congruent, then the minor arcs, are also going to be congruent. So let's take a look at an example here in circle R. Segment AB is congruent to segment CD. And the measure of arc AB, and again, when we talk about measure, we're talking about degrees. The measure of arc AB is 108 degrees. Find the measure of CD, and yeah, because the chords are the same, we can be confident that the measure of the arcs is also going to be same. Moving on, theorem 10.4. Again, we're talking about arcs today. I'm sorry, not arcs. No. We're not talking about arcs today. We're talking about chords today. Theorem 10.4 says if one chord, this one's kind of interesting. If one chord is a perpendicular bisector, let me write that down. If one chord is a perpendicular bisector of another chord, then the first chord has to be a diameter. Splits the circle in two. This is kind of interesting. I'll draw a picture here to illustrate this relationship. So we've got a circle. Oh, sorry, I was distracted. The dog was making some noises, and then I heard something. But anyway, we're in good shape. So yeah, if we've got a chord, so let's just start with one chord, and then let's think about it. If it's going to split it, be a perpendicular bisector, it's going to come in at a right angle, right? A right angle to it, and a perpendicular bisector is going to split it up evenly. You kind of don't have a choice but to go through the center to do it correctly. So that's what they're talking about right there. If one chord is a perpendicular bisector of another chord, then the first chord has to be a diameter. And it turns out the kind of the flip-flop is true. There is a little bit more added information here, so they chose not to do it as a biconditional if and only if. But this one says if a diameter of a circle is perpendicular to a chord, then the diameter, so in this case they're saying that it's a diameter to start with, then the diameter bisects the chord and the arc. So it's kind of in reverse. You know already that it's a diameter, and then if a diameter is hitting a chord, you know that it's going to, I'm sorry, let me back that up. If you know that the diameter is perpendicular to a chord, then that's all the information you need to know that it bisects the chord and the arc there. Okay, couple of examples here. Example 2 is kind of a weird one. It says, you can read through it, but I'll read through it as well. 3 props are placed on a stage at points P, Q, and R as shown. Describe how to find the location of a table so it is the same distance from each prop. This is a fascinating problem. And I'm going to kind of do it halvesies, halfway. I actually don't have my straight edge and compass to do this the proper way. But I'm going to describe, because that's the way they said it, but I'm going to describe how you would go about this. And this is kind of a good skill to have. If you could imagine having 3 different objects, or you could be on a map and you've got 3 different points. You want to be equidistant to them all so that you can theoretically, get to each point equally as fast. Kind of like where you might build your base in order to get to your outposts in an equally quick method. There's lots of applications here. But what we're going to do this is we're going to actually connect PQ and QR and make those segments. And then what we can do is we can draw a perpendicular bisector for PQ. And if you remember, you take your compass, draw arcs, maintain that measure, draw the other arcs. So you'd be like, boom, boom. And then you'd have your perpendicular bisector, which is cool. But because the perpendicular bisector is going to be the diameter of some circle, if you do the same thing to the other side and do a perpendicular, or do the arc, maintain the same measure, do the arc the other way, find out where they cross, then when you draw these 2 perpendicular bisectors, where they meet will be the center point. Because they're both diameters, it will be a center point of a circle that contains these 3 points. So it's a cool thing. It's a cool thing that you can do. So I'm going to write this out. And I apologize, I don't have my tools here to do this appropriately. But it did say describe, so we don't have to actually do it. Find the perpendicular bisectors of segment QP and segment QR, where they intersect, will be the center of a circle containing P, Q, and R. Oxford comma. All right, so it's a pretty cool thing that you can do. And like I said, lots of applications for this. It's nice how that works. And again, it's because those perpendicular bisectors of those chords that you formed are gonna be pass through the center. And if you find out where they meet, then that's gonna be the center of a circle that they both are a part of. So it's a really cool thing, I think. All right, moving along. Example 3 says use the diagram of circle C to find the length of segment BF. Tell what theorem you used. All right, so we've learned 3 today. We'll need to describe which theorem it is. So I'm noticing that we've got a diameter and it's perpendicular. And as soon as we know that, theorem 10.5 says if you got a diameter perpendicular to a chord, then it bisects the chord and the arc. So we're going to know that BF is 10. And yeah, it's theorem 10.5. Now let's write it out just so we got good practice here. If a diameter is perpendicular to a chord, then it bisects it. All right, let's flip it over, see what else we got to learn. Theorem 10.6. Theorem 10.6. And yeah, this is our last chord relationship today. And this one is pretty intuitive as well. You could probably think about chords for a while and come up with this one. In the same circle, I wonder if you guys can guess what the next part's going to be. In the same circle or in congruent circles. Two chords are congruent if and only if, by conditional statement, true front ways and back ways. I'm sorry, I should say true front ways and its converse. If and only if they are equidistant from the center. And again, I think this is a little bit intuitive. If you're on the same circle and the chords are the same distance from the center, just how circles are so round, yeah, these measures are going to be the same. Yeah, it makes good sense, I think. So looking at example 4, circle P, we got PV is congruent to PW. You can tell that with the tick marks. And QR, and that was actually saying the measures are equal. So the measure of PV is equal to the measure of PW. But then they tell us that chord QR there is, its measure is 2x plus 6. And chord ST, its measure is 3x minus 1. And they want us to find the measure of QR, one of them. Well, we can write an equation. Because these distances are the same, we know the chords have to be the same measure. So we can set 2x plus 6 equal to 3x minus 1. Solve that thing, and we get x is equal to 7. That's x, but they're wanting the measure of QR, so we'll plug that back in to QR. 2 times 7 is 14 plus 6. So yeah, QR is 20. The measure of QR is 20. Let's do some more examples. By the way, it might be a good idea to pause this, try these out yourself. But for sake of time, I'm going to dive right in. Find the value of x in circle C. Okay, again, we've got a diameter that's perpendicular to a chord, so we know that those are going to be equal. And, solve it. X is 6. Moving on to example 6. Find the value of x in circle C. Okay, same distance from the center, so the chords are the same. So write an equation and solve that. And we're there. X is equal to 4. And then finally, determine whether segment RS is a diameter. Explain. Okay. Well, what I see so far is I see that RS is bisecting TU. But if I look back through my theorems, that's not enough information to say that RS is a diameter. It has to be a perpendicular bisector. It's a bisector, but it could be coming in at all sorts of different angles here, but still bisecting UT. But we need to know if it's perpendicular, if it's at a right angle to TU. And that, my friends, is what we're going to have to try to figure out. We're not given a whole lot of information here. Well, I mean, I take that back. We've got some congruency marks here. And actually, wait a second. I mean, we've got triangles. I think I'm onto something. Where I'm going to head here is I'm going to do the reflexive property in the middle there. RV is congruent to RV. Then I'll have side, side, side. I'll be able to say these triangles are congruent. And if these triangles are congruent, then corresponding parts are congruent. So angle TVR is going to be equal to the measure of angle RVU. So they're going to be congruent. But they're also supplementary. So guess what the measure of each one's going to have to be? That's right. It's going to have to be 90. So let's get this down. So the first thing is we'll have, it just says explain. It's not actually wanting me to write out a formal proof. So I'm just going to kind of explain it. It's hard for me not to just write out like almost a perfect proof, but we'll assume that we can kind of skip some information here. So I'm going to say triangle RVT is congruent to triangle RVU by side, side, side. So we'll go ahead and just mark it on the picture. If somebody asks me and say, well, yeah, reflexive property. And then from there, we'll know that angle TVR is congruent to angle UVR because corresponding parts of congruent triangles are congruent. And then we know that angle TVR and angle UVR are supplementary because they're a linear pair. Supplementary because of linear pair. So, in conclusion, the measure of angle TVR and the measure of angle UVR must be 90 degrees. Yeah, I wrote a lot of words there. And if it's 90 degrees, then that makes RS a perpendicular bisector. So RS is a perpendicular bisector. So must be a diameter. Woo! Man, I wrote a lot of words. Sorry about that. All right, so if you'd like to practice, it turns out, oh man, I don't have the practice in front of me. But if you check on Canvas, you'll have the practice. Thanks for watching.